And that doesn't look very interesting. Let's go over here. Here we are. So we're right in the middle of this chapter. Surely we'll still be talking about it through kind of Monday. And I can't remember, did I ask you to read stuff for today or for Monday? For today, like the remain. So we're going to keep on going through Monday. We started talking about torque. We still need to practice with it a little bit, but we're also going to talk about several other things today and Monday. So it's sort of a big chapter on rotations. Here is our definition of torque, and there's sort of one torque, but it feels like three different, oops, that didn't work well. Three different definitions. Let's try that again. All right, we had three different ways to compute it, but they all reduce to exactly the same thing if you look at the geometry. I need to know where my axis of rotation is, and I'm applying a force at some point relative to the axis, and the distance from that point to the axis is called r, from where I'm applying the force to the axis of rotation. The force itself is called F. So I can either multiply the length of r times the length of F times the sine of the angle between them. That means if I continue along r, how far do I have to rotate over to get to F? That defines that what theta means there, that particular angle. Or I can take the component of F that's perpendicular to the r direction, that's shown here, and just multiply by the full length of r. Or I can take the component of r that is perpendicular to the F direction. That means I draw the line that contains F, maybe extend it forwards or backwards like I've done here, and look at where, if I take r but just project out the perpendicular component, you know, how far is it from that line to the axis of rotation? That's called the moment arm, or r perpendicular. And we practiced here with this example showing how to calculate it in three ways, and you get the same number. And just a reminder about the sign convention. You don't usually define a sign of torque unless you know which way is the positive direction. And we could choose positive to be either direction. It could rotate around the axis. Here I've chosen positive to be clockwise. It's perfectly acceptable. If I were sitting behind the screen, I would say that direction is counterclockwise. So, you know, there's no universal sense to clockwise or counterclockwise. But in order to get the sign of the torque, the intuitive way to do it is to just say, look at that force. Is it trying to rotate it in the positive direction or the negative direction? And in this case, you know, pretty much everybody would say, oh, I see, it's trying to rotate it the opposite, the positive way. So I put a minus sign in front of the torque. So here's some voting questions. So if you've got your voting cards, take them out. If not, you can use the usual finger equivalents for 1 or 2, meaning A or B. All right, so we're trying to loosen a nut here that is stuck. Oops. And we're going to try to do it two different ways. One is, I think I just flashed the answer on there, but pay no attention to the man behind the curtain. So you can either pull with a certain force on the edge, far end of the wrench, or you can extend the end away from the end of the wrench by a rope and then pull with the same force along the same direction on the end of the rope. Have we succeeded in increasing the torque in this second situation? In other words, are we going to be more likely to loosen that nut or be able to get it to turn? Or is it going to be easier to turn? Okay, some of you are giving the indication you're ready to vote. So we've got A or B or 1 or 2 here. Hold up your fingers if you've got it. I'm seeing both answers, but my sense is that the more than half of them that I could see were B, no. Anybody want to voice the reason for that? I agree. My answer is no as well. Dylan?
I want to say it's B because you're not increasing the radius about the axis nor increasing the force with the rope. So I just didn't think that.
Yeah, so if you're calling the radius that's R actually has increased, right? R is from where you're applying the force, that distance from there to the rotation axis. So this would be R in the first situation. R would be actually bigger in the second situation. So that seems maybe promising. Maybe we're going to have a better time of turning it in the second case. Even though R is bigger, notice that F here is tilted at an angle to R, whereas it was perpendicular to it before. So that's different too. Amelia? That's probably the easiest way to think about it, right? What is the definition of the moment arm? It means you draw the line that contains the force vector, and you say, what's the perpendicular distance from that line to the rotation axis? And in the first case, that's clearly the length of the wrench. In the second case, if I draw the line that contains the force vector, it's still horizontal, and that perpendicular distance is still the length of the wrench. So if I look at the first form of the torque, the third form right here, force is staying the same, the moment arm is staying the same, so the torque is the same in both those cases. Otherwise, if you had a really heavy door, you'd see people attaching ropes to it to try to open it, but we obviously don't do that. You've probably never thought about, why is the handle here, but they don't put the handle in here, right? If the doorknob were here, it would be really hard to open and close the door. There's a good reason that it's always at the farthest point you can attach it from the rotation axis. Sarah? Yes, so the question was, how do we find the moment arm? And the answer is you always draw the line that contains the force vector. So wherever the force is being applied, draw it out into a line, and then calculate the perpendicular distance from that line to the axis of rotation. So that would be this distance. Let me see if I have it drawn in one of these cases. Yes, so here is the force being applied. Here's the line that contains it, shown as a black dashed line. And then how far is it from that line to the axis of rotation? In other words, the shortest distance I can draw is that perpendicular distance. That's the moment arm. So always draw the line that contains the force vector, and we'll get more practice with that soon. Other questions on that? Okay, one more voting question based on the same images here. You're using a wrench and well, actually, this one isn't a voting question. We have to rank them. So you're going to have to tell me in words what you think about it. You're using a wrench and trying to loosen a rusty nut. Which of the arrangements is most effective in loosening the nut? List in order of descending likelihood of effectiveness. So which is going to be the most effective at loosening the nut? What do you guys think? Somebody just tell, we don't have to vote on it. Jaden? Yes, and one way to see that is, it's kind of the same argument we made before. The moment arm is this huge distance here. If I draw a line that contains the force, the moment arm, it's hard for me to do this straight here in midair, but this is the distance of the moment arm. So I've made a huge moment arm there. It's the same force being applied in all cases, but it's just being applied different ways. So it's certainly bigger than this one, which has a shorter moment arm. We already discussed that this one hasn't changed anything a bit, right? So these two are sort of a tie. And this one, the moment arm would be from the line that contains that force vector. It's hard for me to do that here, but from there down there. So the moment arm is even shorter in 3. So the correct ordering would be 2 is the most effective. These ones are less effective. They have a shorter moment arm. And then if I tilt it at an angle like this, I'm making the moment arm even smaller, that perpendicular distance to the line that contains that. Okay, any questions on those? Crucial idea, be able to visualize the moment arm. Or sometimes you can just visualize the perpendicular component of F. It just depends on whatever you see first. So let's do a worksheet. For those of you on Zoom, this, I can't remember if it was posted for yesterday or Monday. It may have been yesterday, worksheet 2. I don't know. You may have to click, but it's got these weird wrenches on it that have a bend in it. There's no good reason to do that, but I just thought, well, it'll make the calculations a little bit more interesting. So we're going to try to loosen some rusty nuts with bent wrenches. So just go ahead and try them. I'll try to give you enough time to at least work on one or A and B. So in all cases here, the axis of rotation is where the bolt is at. That's the thing that's going to do the rotating if it started twisting. The axes aren't labeled, but if you look up at the top, the X and Y are labeled in meters. So is what? Yes, it does, because so one of the definitions was R times F perpendicular, or F times R perpendicular. So force is in newtons, SI units, and R is in meters. So it's in Newton meters. Okay, so in A, we're applying a 10 Newton force at the end of this L-shaped wrench in the direction straight up in the screen. How can I calculate the force, the torque that generates about the center of the bolt there, or the nut? I mean,
You draw the triangle and find the hypotenuse.
Yeah, so I certainly could use the Pythagorean theorem and find this distance right here. I think it's being suggested, and that is what we would call r. R means the distance from where you're applying the force to the rotation axis. I claim that, although there's nothing wrong with doing that, and you could use that in 2 of the 3 forms, that's not the easiest way to do it here. Arthur? Yeah, so I can visualize what the moment arm is here if I draw a line that contains the force vector. So I'm going to use the form that's F times R perpendicular, F times the moment arm. Here is it shown in the dashed red line. That's the line that contains the force vector. And I want to find the distance from that line to the center of rotation. That's what's called the moment arm. I'm showing that as the green double arrow head thing there, right? When we say the distance from a line to a point, we always mean the perpendicular distance, the shortest distance you could draw. So in this case, that's just, you look down the scale here, the moment arm is 0.3 meters, right? And in this form, I just use the whole magnitude of F. So F is 10, R perpendicular is 0.3, so 10 times 0.3 is 3 newtons times meters, Newton meters. The other ways should give the same answer. They're just a little bit more work because you're doing the Pythagorean theorem, and then you might have to find F perpendicular or figure out what the angle is. It's going to be a lot more work, I think. In this case, I would be highly motivated to use this form and not one of the other ones, although that's not always universally true. How about the second case, so here's B, and I know some of you just started working on this when I started talking again. What form of the torque do you think would be most useful in this case? I agree, F times R perpendicular, and in this case, I'm drawing over here the line that contains F, again, as red dashed. And then R perpendicular is how far from that line to the center of the nut. So that's this distance. That looks like 0.1 meters is the moment arm there, right? So it's 10, I didn't read the question here. Let's see. In the same configuration, suppose you decide to try pushing the end in the minus x direction as shown. It sort of feels like you'd have to push harder. And in fact, we will have to push harder. So we're going to, with what force must you push to generate the same torque in A? So I want this torque to end up being 3 Newton meters. And the question is, what F do I need to do that? And my R perpendicular, I partially obscured the scale there, but it's 0.1 meters, right? So I want 3 Newton meters to be F times 0.1 meters. And when you divide by 0.1, you multiply by 10. So that gives F is, ooh, that's a mistake. This should be newtons, not Newton meters. F is 30 newtons. That's a typo there, or scribble-o. 30 newtons for that one. Okay, any questions on B, Arthur?
Yeah, I'm having trouble finding R through the diagrams. Like for A, where would R be? It's like the
With not R perpendicular, but just R. R is always the distance from the point where the force is being applied. So that's from here to the axis of rotation. So it would be that diagonal distance that Edward Lee was talking about. Same thing in this second one here. R would be that diagonal distance from the point at which it's being applied. That's the end of the wrench to the nut. Yeah.
So I'm kind of confused whenever like on B we're drawing the line and the difference is 0.1. Why does it not have like a negative?
Well, so in this case, when someone says, what's the torque? We tend to just give the magnitude of the torque. I didn't specify a positive rotation direction. In order to give a sign to a torque, we'd either need to say counterclockwise is positive or clockwise is positive. So, if we said counterclockwise is positive, then both of these would be positive torques because they're both trying to twist it around in the counterclockwise direction. It's just when that's given. Yeah. Otherwise, it's sort of like when you push on an object, I might say, well, I know how big the force is because I measured it. But if you ask me for the force X component, then I've got to say, well, wait a minute, which way is plus X? You could choose it either way. Same way here, right? I know how hard I've got to twist it, but if you want to say the sign, you got to tell me which way is the positive twisting direction. The positive direction is usually by convention the direction we're going to call positive, increasing angle direction, which means positive omegas would be twisting so that angles are increasing and so on. Positive torques are going to correspond to trying to twist it in that direction. Okay, third one, for some inexplicable reason, we decide to apply a 10 Newton force at an angle of 30 degrees from the horizontal at the elbow point. What magnitude torque are we generating here? So again, we're not trying to match the torque we calculated in A, but just saying, what is the torque? What form do you think might be the most useful here? F times R perpendicular, or F times moment arm, R times F perpendicular, or FR sine theta? Yeah.
I did R times F perpendicular.
Yeah, I agree because, well, first of all, if I want to visualize what R perpendicular is, I've got to draw this weird line that goes through there, and then I've got to figure out what that perpendicular distance is. It's not immediately obvious to me what it is. You can figure it out using a little bit of geometry, but that's not so obvious. The second one, which is R times F times sine theta, I have to draw that R vector in and then keep going along that direction and say, how far do I have to turn here? Now, I should say this angle doesn't look much like 30 degrees, it looks more like 60 degrees, but take me at face value. I'd have to figure out what angle this is off the vertical. That would actually be 60 degrees here, if you believe my numbers on there, which is sort of doable. But the easiest one by far, given the information that we have here, is to say, what is the component of the F perpendicular to the R direction? In other words, project F onto this direction. That's just 10 cosine 30 to get the projection of F onto the horizontal direction, or the horizontal component of that. 10 cosine 30, and then I multiply that times the full R, which is 0.1 meters. So we're using F perpendicular times R. 10 cosine 30 times 0.1 is 0.866 Newton meters, approximately. Yes, Amelia. Yes, I can, and I'll try to do it with the pointer here, even though it's hard for me to hold it steady. To find, well, in this case, R is just by definition, the symbol R always means how far from the point where you're applying the force to the axis of rotation. So it's that distance there, which is 0.1 meters. So think about where you're pushing with the force on the object, how far from there to the point it's rotating about. That's always what R means. R perpendicular, the moment arm, is more complicated, right? It would be, I have to draw this line through the force vector and figure out how far it is perpendicular to there. That would be a different distance, which we could figure out, but there are easier ways to do it. Questions? Any more questions on that one? Yes. Well, so when we say perpendicular, this is a shorthand notation. You have to ask yourself, perpendicular to what? So when we say R perpendicular, we mean the component of R that's perpendicular to F, right? Draw the line that contains F and project out R perpendicular to it. So that's what we call the moment arm. Here, when we say F perpendicular, the component of F that's perpendicular to what? Perpendicular to the R direction. So here's the R direction. The direction perpendicular to the R direction is horizontal. And if I want to project out the horizontal component of this, right, it would just be to get from the tail to the tip, I move horizontally and then vertically. So we just want that horizontal component. So I'm thinking of this little right triangle there with a 30-degree angle in it. Yes, R perpendicular is if I draw this line here, which it's hard for me to point with my pointer, draw that line in and then get that perpendicular distance there, which isn't immediately obvious what that's, it's going to be less than 0.1 meters. And I'd have to think more about it. to get it. So we're trying to choose the one that requires the least thinking. And I'm just looking at this thinking, oh, if I draw in this little right triangle here, I can see what F perpendicular is. Perpendicular means perpendicular to R. And R perpendicular here means the perpendicular component to F. Okay. Other questions on that? All right. Now let's talk a little bit more about torque. Not only, so we've been talking as if there's just a single force being applied at a certain point on an object that's pivoted to rotate about an axis. But oftentimes the force is distributed. For example, here's a beam right here. Gravity's, oh, something went wrong with my pointer. Try to reset there. It's pivoted to rotate about some hinge vertically. And so if we let it go, it would flop down, you know, and slap into the wall or something like that. So the question is, well, gravity's obviously trying to twist it in this downward direction here. How much torque is it applying? Well, it's sort of complicated because, well, and in what follows, I'm going to assume the clockwise direction is positive just for definiteness. Clearly, gravity's trying to turn it in the clockwise direction, right? It's trying to twist it down and around like that. So I just chose the positive direction to be the way that gravity's trying to turn it. Here's why it's complicated, because gravity's not pulling, the Earth's gravity isn't pulling on any one point on here. It's pulling a little bit on this mass, and it's pulling a little bit on this mass, and all the way to the edge. And they all have different moment arms, right? There's little bits of forces that are distributed all along the object. So it seems really complicated, right? Now I don't just have one force and one moment arm. I've got lots of little forces being applied to little bits of mass, and each one has its own moment arm. It sounds like a nightmare or a problem from calculus if you've done that kind of thing before, but we're not going to do that. We're going to try to simplify it. And we obviously can. So we're imagining gravity exerts a force, you know, I'm going to divide this up into a bunch of little tiny bits of mass. Mass one is already all the way out at the end. So the gravitational force on it is m1g, m2g on the second bit of mass, and so on. So there's lots of forces there. To get the total torque, I'm going to add up the torques due to all those little bits of force, because each one is contributing to trying to twist it around the axis. To calculate the torque, I need to multiply this force times the moment arm. And the moment arm, notice that this is perpendicular kind of to the direction of the beam. And therefore, the moment arm for M1 is this distance. Let's just call that X1 as I'm showing there. The moment arm for M2, for that M2G force, is X2. I'm just going to call it X2. So I've got to add all those up. Each one of those little forces is contributing a little bit of torque. And to get the total torque, we have to add them all up, which again, looks like a nightmare, but we're going to simplify it. First step is there's a common factor of little g in each one of these. So let's factor that out in front. The second step is a little bit of a trick. What I'm going to do is multiply by the total mass of the beam, but also divide by the total mass of the beam. So I haven't done anything, right? I've just multiplied by the same thing in the numerator and denominator. Okay, so M, the capital M here is just shorthand for the sum of all the masses. That's just the total mass of the beam. And then we're going to look at everything except the capital M times G. So I have all this stuff in the parentheses divided by capital M. We're going to define that to be something called the x-coordinate of the center of mass, if the x-axis is horizontal, as I'm kind of suggesting here. In terms of if I can figure out where the x-coordinate of the center of mass is, and here, you know, whoever drew this picture that I stole from the web is, they're suggesting the center of mass is where this little black and white circle is right here, right? Because the center of mass is sort of like, as we know from lab, when we took that little arm, the ballistic pendulum that was going up, it's the point you could balance it on if you put a little blade underneath it. Well, look, there's more big pieces of mass over here and less little pieces of mass over there. Maybe I could balance it there. That seems like a reasonable thing, right? Because it's thicker at the left. In any case, in terms, if I define this ratio here to be the x coordinate of the center of mass, then the net torque seems simple. Well, if I can figure out where the x coordinate of the center of mass is. So notice that this looks just like a single force is acting. It's as if the weight of the entire beam, that's the total mass times g, that's the weight of the entire beam, is being applied at this point. I can pretend that total force, even though the force is being applied all across it, I can just pretend it's all being applied here. And this x center of mass is the corresponding moment arm in that case. Okay, so what I've got boxed down there is the shortcut method. If you need to calculate the gravitational torque on an extended object, you can pretend the entire weight force, total mass times g, is exerted only at the center of mass and use the corresponding moment arm. And calculating the center of mass can sometimes be a pain, but the nice thing is for nice symmetric objects, like if you have a meter stick, center of mass is always at the center of symmetry of it. If you got a sphere, center of mass is at the center of the sphere, as long as it's a uniform sphere. If I've got a uniform meter stick, it's halfway down the meter stick. If I've got a circular disc, it's at the center of the circular disc. Yeah.
Are we only going to look at objects like the center mass?
Yes, all the objects we'll look at in physics 110, generally if they're not symmetrical, you have to use calculus to figure out where the center of mass is. So in our cases that we'll use, they'll always be symmetric objects and it's always at the center of symmetry of the object. So it should be clear, and you'll see several practice problems where we use that. Okay, so let's look at another example. Here's one that's not just a one-dimensional bar, but a two-dimensional. I'm imagining this is some sort of cutout, maybe of wood, a thin piece of wood that's cut out into a weird shape, pivoted to rotate about an axis that's coming out of the slide or the screen right here. And we want to know the torque due to gravity. And so what I'm going to do is divide this up into a whole bunch of little masses. And I'm going to try to locate where the center of mass is. Now, in this case, it's not a symmetric object. It's not obvious how to find it. But if somebody tells you where the center of mass is, in other words, I put some x and y axes on there, I can calculate not only the x coordinate of the center of mass, but the y coordinate of the center of mass as well. And then the claim is the same. I can take the total mass of this object, and therefore the total weight force, and just pretend that it's all being exerted at the center of mass. We know that's not true. Little bits of force are being exerted on all the little bits of mass all over the place. But we can calculate as if the entire force on the entire object is being exerted at the center of mass. And so that's a great simplification for calculating torques, where the force is sort of distributed over the object. So in this case, the relevant thing is if I knew where the center of mass was, I know what the total force is, the moment arm would be this distance. And if somehow I knew the moment arm, I could calculate what the torque was, right? And if somebody gives me a sign for which way is the positive rotation direction, I could even put a plus or minus sign on it, okay? So even in two-dimensional cases, if you know where the center of mass is, and we're always going to do symmetric cases, so it'll always be obvious where the center of mass is, you just pretend the entire force is being applied at that point where the center of mass is located, the entire gravitational force, and that will give you the torque. Okay, if this were a counterclockwise is positive kind of convention, everybody okay that this is trying to twist it clockwise? If we just imagine it as a single force generating the torque, and therefore I need a minus sign here because it's twisting it in the negative direction. Okay. Now, we're going to develop the F equals ma of rotational motion, right? Just like torque is the analogy to force, but for rotational motion, alpha is the analogy to acceleration. And so that just like there's a relationship between F and A, there's a relationship between torque and alpha. And that's what we're going to try to figure out right now. Again, I'm going to imagine, just some arbitrary shaped object and a definite axis of rotation. And let's just focus on one tiny little bit of mass on there. So I'm going to say, here's a mass M1. It's just one of those little tiny squares I've got on there. And there's some net force that's being exerted on it. And by net force, I mean, well, maybe someone's attached a little string to that mass, but certainly the neighboring bits of masses are also pushing on it because they're attached to it, right? So they're going to be pushing or pulling on it in various directions. When we take all of those forces into account from the neighboring bits of mass, and even if you've attached a little string to it and you're pulling on it, this is the net force that that little bit of mass feels, okay? Now that mass, as this thing rotates, is going to be moving along a circular arc, right? And that circle will have a certain radius. Since I'm calling this mass 1, I'm going to call that radius R1 of the circular arc. And I'm going to draw the direction, at the instant that we're considering this net force right here. Let's draw the direction that's tangent to the circle at the location of mass, okay? And I'm going to calculate the tangent component of the net force, okay? Just bear with me for a second. So I'm going to take the component of that force that's tangent to the circle. And in this case, we talked about earlier that well, certainly if we think of F net equals ma components for this mass right here, we could certainly do the tangent component. We could also do the radially inward component, but here I'm just writing down the tangential components, and you'll see why in just a second, because it's this tangential or perpendicular component of the force that comes into a torque, and I want to convert this into a torque. Let's multiply both sides by this radius here. And now you see I've got something that looks like this is the net force being applied to M1. And when I calculate the perpendicular component of that force times this distance, that gives us the little bit of net torque that is due to the net force that's being applied to that one. Okay, and it ends up it's equal to M1 times R1 times A1 tangential. All right, hold on just for a second. So that's the torque being applied to this just by virtue of the forces that are being applied to M1. Now we're going to do that for all the other bits of mass on there, and they all work out the same way. Here's M2. It's going on its own circle, radius R2. Let's add it in, an M3 and M4. When we do that, we're going to get a whole bunch of these identical terms. And the total torque, if we add it up for all the bits of mass on this thing, this will be the net torque due to all the forces that are being applied on all little bits of mass. Okay, so we'll call this tau net. And that's equal to a bunch of stuff. Notice in each one of these terms, the alpha is the same because alpha is the resulting angular acceleration of the entire thing. There's only one alpha. There are lots of m's. There are lots of r's, but there's only one alpha. So I can factor that alpha out of the entire thing. And I guess I went too fast here. I'm using the fact one of our relationships between linear and angular quantities, the tangential acceleration is equal to r times alpha. So I'm using a1 tangential equals r1 alpha, making that replacement there. And there's only one alpha for all the bits of mass. Okay, so the left-hand side is the net torque being applied to this object. And the right-hand side is something times alpha. This is like F net equals something times A. That something is important because it's like our rotational analogy to mass. Yeah. Well, alpha is the angular acceleration of this thing about the axis. Well, it's not anywhere. When I have an object rotating about an axis, we just look at the entire object and how its angular velocity is changing to get the alpha. It's not located in any one place. We would say, hey, this particular bit of mass has a definite acceleration, and you might want to locate that acceleration at that bit of mass. But when you have an extended object like this that's rotating around the axis, the alpha isn't located anywhere. Just like the omega isn't located anywhere. When something's rotating at a certain rate, you wouldn't say that rate is happening right here. Well, that's sort of the whole thing that determines the omega. So again, this is torque net equals something times alpha, like F net equals ma. This is important. This is the analogy to m, or mass, for rotational motion. m1 times r1 squared plus m2 times r2 squared. It's the sum of all the bits of mass times the square of their distance from the rotation axis, added up for all the bits of mass in there. So it's called the moment of inertia, as you read about in the book, or I can't remember, some books also use the term rotational inertia. They mean the same thing. And the rotational inertia is kind of like, mass tells us how hard it is to get an object accelerating linearly. If I want to test the mass and I'm in outer space, I try to accelerate it and I see how hard it is. The harder it is to accelerate linearly, the bigger the mass. It's the same way with rotational inertia, or moment of inertia. I take an object that's ready to rotate and I try to get it rotating. The harder I have to work to get it rotating, the bigger the moment of inertia. So, if I have a little cardboard cutout disc and I want to start spinning it, it's really easy. And so that has a small moment of inertia. If I go to the gym and I get one of those big barbell plates, right, and I really have to heave it to get it going, right, and then it starts spinning around the bar, that would have a larger moment of inertia. A tire on a car would have an even larger moment of inertia. A Ferris wheel is going to have a huge moment of inertia, right? It's really hard to get it turning. Okay, so it depends on not only the bits of masses, but how far those masses are from the center really makes a difference, because it's being squared, right? So if I take the same bit of mass and I move it from here to way out there, I've greatly increased the moment of inertia, right? Because that little mass, which it was being multiplied by a small radius squared, is now being multiplied by a big radius squared. And so I've changed the moment of inertia a lot. Okay, so this is F net equals ma. But it's the rotational version. Torque net equals I alpha, and I is sort of like mass. It tells you how hard it is to get something going, but in a rotational sense. Okay. Again, there's a convention for torque here. If we have a positive direction for rotation, then we can say whether torque is positive or negative. Just like we have a convention for alpha. So when torque is positive, alpha will be positive. When torque is negative, alpha is negative. And notice that both of these things on the right-hand side are properties of the entire object. The rotational inertia isn't a property of a certain point on the object. It's like the whole barbell has the property of rotational inertia. And there's only one alpha for the rotate, at any instant if I'm trying to get it twisting. Okay, let's do voting question to start with, or two maybe, I can't remember. Here's our definition, just to remind ourselves of moment of inertia down at the bottom. I've got a meter stick, and I'm going to consider setting it up to rotate around an axis through the center, the 50 centimeter mark on the meter stick, or about one end. How do the moments of inertia of the object about the axis compare? In other words, you may have some intuition about this. Is it going to be easier to get this rotating at a certain angular speed, or harder compared to what you have to do to get this one rotating at a certain angular speed? Ideally, we want to figure out from this formula which one is going to have the bigger moment of inertia. But intuitively, moment of inertia is how hard it is to get it spinning around that axis. I should have brought a meter stick so that we could pass it around and you could actually try twisting it with your wrist, because you can kind of tell. In this case, these aren't really uniform rods, but you may have the intuition. If this thing's pretty hefty, it's easier to rotate it around the center than it is to rotate it around. I'm really like working my wrist here to rotate it around one end. The question is, so the answer is, it has a larger moment of inertia around the end axis. And the reason I put this in here is I wanted to discuss how to think about it with this formula. Well, if you think of the left-hand parts of the mass and the right-hand parts of the mass here, notice that this piece that I'm showing in gray here is kind of the same. All those bits of mass are the same distance from the axis in the gray piece on the left and the right. So that adds up to the same moment of inertia. It's the green part that's changed. And notice the difference between the left and the right is all these bits of mass are closer to the axis on the left than they are on the right. And therefore, all those R's corresponding to those same bits of mass in the green piece are bigger on the right-hand side. So I'm going to get a bigger moment of inertia when I add them all up. But again, intuitively, it's just how hard it is to get it going. When you put mass really far away, it's much harder to get it going. Okay, questions on that one? Oh, and this is a demonstration that maybe someone can help me with this. If you watched the videos, then maybe you had a spoiler. But here are two rods. They both have exactly the same mass. I'm just going to ask someone to kind of assess that. Anybody want to volunteer to tell me what they observe when they're moving these around? It's not a trick. Nothing's going to explode. All right. So first of all, you're going to hold them in the centers and just kind of lift them straight up and down and see how the mass compares. They're supposed to be exactly the same mass. Okay. Now, take them both and try to rotate them and tell me what difference you feel between the two. Yeah, this one's harder to move, harder to get rotating at a certain speed, and this one's much easier. They have exactly the same mass. So what do you think the difference is about how the mass is distributed in these two? This one's easy to move. This one's hard to move. Same mass though. Well, actually the center of gravity or the center of mass is the same. It's exactly in the middle because I can balance it in the middle of both of these. Go ahead. Yes, the blue has the mass on the ends. When I take the same mass and I move it farther from the axis of rotation, I increase the moment of inertia because those R's are, the little bits of mass are the same, but we put them at bigger R's. And it's being squared, so the effect is really magnified, right? You don't just make it bigger, you make it bigger like a square. So in this case, one of them, I'll pass them around. We've got enough time. You can give them a shake. You can actually see where the masses are. This one's got nothing in the middle, but you can see the mass is there in the end, and this one, they're in the middle there. But should be able to tell. Yeah.
So with we're looking at the torque net equals the moment of inertia times alpha.
Yes.
Will we be given the moment of inertia in a problem?
Yes, what we're going to talk about, we have a table of moments of inertia that's in the book, and it's for nice symmetric objects like, a uniform disc kind of wheel or a uniform ball, like a bowling ball, that kind of stuff. So yes.
Things like the XCM as well.
Yeah, well, the XCM, all the cases we'll be dealing with a totally symmetric object. So it'll be at the center of symmetry of the object. So yes, you won't have to worry too much about those. Ah, well, that was the perfect intro to this. This isn't from our book, but you have almost the same table in your book. This is telling so here is a uniform cylinder, which is pivoted to rotate about its axis of symmetry, which is going through the center of that cylinder. Okay, and we're imagining that this entire thing has mass capital M, and the radius of the cylinder is R. Its moment of inertia is 1/2 times M times R squared. Notice the moment of inertia should have units of mass times distance squared, so that kind of makes sense there. But the factor of 1/2 is maybe kind of surprising. It's different than other things. Okay, here's a hoop that is pivoted. This again is going perpendicular through the center of the hoop, and the hoop is going to start rotating around that axis in the direction perpendicular to the rotation axis. And its moment of inertia is not 1/2 mr squared, but just mr squared. So that means if this object had the same mass as this object and the same radius, this one would be harder to get moving. Notice because some of the mass here is near the center axis, whereas all the mass is really far away. Again, the radius of the circle is are there. So we've got a solid sphere. We've got, yeah, we'll never use this one, but thin spherical shell. This is like, just all the mass is on the outside of the sphere. It's not distributed through the center. And then here's two that are a little bit different. This is like our meter stick, right? This is a rod pivoted to rotate about the center. And here's our meter stick or a rod pivoted to rotate around the end. And notice that this moment of inertia is 4 times as big as this moment of inertia. So it's quite a bit bigger. And you'll notice that if you take a meter stick and try to rotate it around the end versus in the middle, it's easier in the middle. Okay, that was to remind me to point that out. Okay, so if you're rotating about the end, you're going to need this in the voting question. It's 4 times as big of a moment of inertia as it is about the center. 4 times as big. You need to know that for this question, but I've lost control again. Here's a meter stick with a rotation axis at its center and the same one with its rotation axis on the end at the right. If a force F is applied in the direction out of the screen at the location shown on the left stick, where would we be able to apply the same force and have the same angular acceleration result? We got to think about torque net equals I alpha. We want alpha to be the same in both cases. I is not the same, and so it seems like torque is not going to have to be the same. So can you reverse engineer where to put F? It's one of the answers that's given there. Again, you have to use the fact that the moment of inertia is 4 times as big in this case as it is in this case, right? So I is 4 times bigger, and we're doing torque equals I alpha. The torque is just due to that one force. All right, let me just see. I don't know if there's confusion throughout. People aren't necessarily giving a strong sign that they're ready to vote. Okay, I'm seeing 2s and 5s. 5s is probably the most popular one, so that's E here. Anybody want to explain far end of the axis? How are you getting that?
I viewed like on the first one, the F being like 1/4 the way, so that times 4 is 4 on 4. So just put at the very end, away from the like the axis of rotation.
Yeah, I mean, so in this case, this distance is, F is coming out this way, so this is our perpendicular in that case, right? So we're going to say the torque equals I times alpha. And let me just solve for alpha, because alpha is going to be the same in both cases. That's what we want to be, right? So we could say alpha is equal to the torque over I. Okay, so in the left case, we'll call that 1. It should be the same as when I take the ratio of these in the second. I'm not sure what I'm doing there. 1, 1, 2, 2. There, that's what I meant to do. Okay, and the moment of inertia as we go to the right case is 4 times as big. And so that means if I want alpha to be the same, right? If these have certain values, denominator got 4 times as big, the numerator better have gotten 4 times as big, right? Now we're using the same force, so we got to have 4 times the moment arm, right? In order to make the torque 4 times as big if the moment of inertia is 4 times as big. I don't know. This one may be just a hair too tricky to do in your head. You have to kind of write down something at least to make sense of it. But in this case, 4 times the moment arm, that means the far end of the axis, because notice in this case, the moment arm was 1/4 of a meter as was stated. And that means the moment arm has to be 1 meter here. So you have to apply the force all the way at the end. All right, good place to stop. And on Monday, we will do a worksheet practicing with some torque net equals I alpha stuff.